Okay.
Welcome, Dr. Devi Prasad Dogra. So today is the concluding day. Am I audible?
Yes, audible.
Yes. So today is the final concluding day of the 1-week faculty development program on artificial intelligence in advanced machine learning and cloud computing, AIAMLCC 2023, organized by the Department of Computer Science and Engineering, Haldia Institute of Technology, held from 10th to 14th July 2023. So today we have on our panel an eminent speaker, Dr. Devi Prasad Dogra from IIT Bhubaneswar. So Dr. Devi Prasad Dogra is the Associate Head of Computer Science and Engineering and Associate Professor, School of Electrical Sciences, IIT Bhubaneswar. He received his PhD from IIT Kharagpur in 2012, MTech from IIT Kanpur. And so he has worked with Haldia Institute of Technology during 2013 before joining IIT Bhubaneswar. He has published more than 120 research papers and patents in international journals and conferences in the areas of visual surveillance, augmented reality, intelligent transportation systems, computer vision, and healthcare analysis. He is a member of IEEE. Currently, he is officiating as the secretary of IEEE Bhubaneswar subsection and editor of SN Computer Science and JMIS journals. So he's heading the IIT Bhubaneswar Research and Entrepreneurship Park, a Section 8 company of IIT Bhubaneswar. So today, Dr. Dogra is going to deliver his talk on applications of AI and ML for visual surveillance. Over to you, Dr. Dogra.
Yes, good afternoon. I'll just take 1 minute time. I am on a call. I will come back. Just 1 minute. Yeah, sorry. So, good afternoon to all of you, and thank you, Haldia Institute of Technology, for inviting me for this talk. So today I shall be talking on a topic which many of you may be working in this field, and many of you might have worked into this domain. So let me first share my screen, and please let me know if my screen is visible or not. Is my screen visible?
Yes.
Okay.
Yes, sir. Yes, sir.
Yeah. Thank you. I'll just switch off the camera. Come back to again. This one. Yes. So I hope my screen is visible. So as I told you that today I shall be talking on a topic which may be of interest of many of you, and some of you may be working on it. So it's basically application of AI and machine learning for visual surveillance, on which I would like to speak. So I would request you, if you have any questions during the talk, you can raise your hands, or we can also have the question and answer at the end of the session. So am I audible clearly to everyone?
Yes,
Yes, sir.
yes.
Yes, sir.
Thank you. Thank you.
Yes.
So computer vision and its relation with the visual surveillance is one part which we'd like to explore more. Okay. Basically, computer vision can be considered as the science and technology of how machines actually see, which is primarily concerned with the theory for building artificial systems that obtain information from images, whereas these images can come from many sources. It can be visible light camera, it can be infrared camera, it can be medical imaging. Even we can get multi-dimensional data from various kinds of sensors like scanners, like CT, MRI, all these images. Whenever we get these sort of images, our objective is to understand these images and try to figure it out that what is the content, and probably from the content we take some decision. Okay. So this is what computer vision does. Why it is important and why it is complex, let us try to understand. So since it makes computers to understand images and videos, when we show an image like this, we need to explain it that what this image contains, whether it is one natural scene, or it is a parking lot, or it is a park, or it is something else, or a city center, something like that. So this one, these are the questions, and you can actually ask many such questions to the user who is looking into that image and try to get the answers given by the user. Now, one point is very important here, that if these answers are varying from user to user, how do we deal with them? Now, this is perfectly fine when I ask the same question to 10 users about an image, and if all the answers are slightly different. Okay, there is nothing wrong in it. I mean to say, this is a perspective. This is from human perspective. A particular person may look into the image in a different perspective. Another person may look into the image in another perspective. So this is definitely going to change, and this change is good, and sometimes this change is also difficult to handle with computers. So, for example, you can ask a question like that: what kind of scene is this? How many cars are there, or where are the cars? You can also look how far is the building. These are, a few questions. You can ask probably thousands of questions out of the same image, and all these questions, if answered by many people, you will get probably different answers. Okay. Now, when you want a computer to answer these questions, you want rather a more generic answer, which is true in all sense. That is what basically we would like to see, that how in today's world, how computers actually are solving this. Okay. Now, going further, let us try to understand, in any such computer vision systems or visual surveillance systems, what are the main components which are involved. So you see that I have shown only 3 components here, which are major components. Like we need a computer which does the scene interpretation. So where basically the brain stays there. You can assume that all the algorithms are implemented inside that computer, and the decision is taken by the computer. So it's basically the brain of the entire setup. Whereas the camera, it's nothing but a sensor which basically senses the environment. Like our eyes, we look into it, we see through our eyes, and that data gets transferred to the brain, and then the brain analyzes things. And the other one is the scene, which is obviously it's needed, because with the scene only we see that the sensor actually gets the data from the scene itself, and that data gets transferred to the computer where the interpretation happens. So these are the primary components. Now we shall actually ensure that how this scene interpretation, which requires a lot of machine learning, artificial intelligence, how it can be done sophisticatedly, and I'll say that rather we make the computer is more like a human. So if you, all of you are might be knowing the Turing test, where we decide that when a computer is intelligent or artificially intelligent. So you know that when a person cannot determine that the answers are given by a computer or a human being, then we call that, if the other side was a computer, then computer is artificially intelligent. Or so we always compare it with human intelligence. So whenever this particular computer tries to analyze a scene, we would like to see that how the analysis is close to the human analysis. Okay. Now, applications are many, like you can apply it in smart cars, like Google has tried it, since maybe 15 years back, or 13 to 12, 13 years back, they have started implementing this. Try to understand that how autonomous driving can be implemented. Even though we have not reached a state of the art where we can completely rely on autonomous driving, maybe in a restricted environment it is possible, but obviously in a crowded environment still we are not that accurate enough to ensure that an autonomous vehicle with the help of computer vision and other sensors can actually run on Indian roads. Okay, so we may be maybe another 20 years, lagging into that respect. So maybe down the line in next 20 years, we'll see that all the vehicles which are moving on the roads, they are basically driven by AI algorithm. Okay, you don't need a driver to sit and to control the vehicles. So this is how it can be useful. Now, I will not show much more examples. Let's try to understand that how do we make the computer intelligent. So to make the computer intelligent, we want the machine to learn things which are happening around us. So that's why the terminology machine learning is becoming very important here. So which actually deals with developing algorithms to allow computers to learn. Okay. Now, in this particular talk, we will rather use a narrow definition of learning. So here we mean to when we mean learning is nothing, because we are dealing with images which are rather than anything other than pattern. We are talking about patterns and objects which are nothing but patterns or shapes. So let's try to link the learning part with respect to these sort of tasks. Here we will use the definition of learning like, we want to learn for assigning objects or an example with some categories. These categories are actually called class. Okay. So this is actually called the pattern recognition. So for example, if you take this face image, you say that, okay, whether this is a teacup or face or phone, obviously we want an answer that this is a face image. Now this is one level of pattern recognition. Now next level can be, okay, this is a face. I want to identify that what is the characteristics of the face. You can say that, okay, the face is smiling, and probably the face is of Bill Gates' face. So all these are more detailed informations which can again further come while we basically deep dive into the framework. Now, how the learning can be classified? So we can classify learning many ways. So one of the classifications is supervised, where the machine learning task is for inferring a function from labeled training data. If we learn the function, then its job is done, because I know that function is nothing but it's a kind of mapping. We give the input, it basically produces the output. But how do we learn the function parameters? This learning can happen through labeled data, because if I know that during training that these are the data which are labeled with X, Y, Z, I know that, okay, if this is the data which is labeled as X, next time I see a data like X, something like this, I will tag it with X. This is called basically supervised learning. Whereas in unsupervised machine learning, it involves tasks of inferring a function to describe a hidden structure. where we don't provide any kind of labeling. We rather, you know, aim to discover the hidden structures within the data, which are complicated. There are some complicated algorithms. I'll show you some examples that how basically unsupervised learning can be done. But people are also working on, and in many applications, it is also possible that you may not get sufficient number of labeled data. Then how do you ensure that the model actually learns it? So in between, when you do not have sufficiency of data or data insufficiency, when you have data insufficiency, then you can actually implement a semi-supervised thing where learning is the task is which also uses unlabeled data for training at the same time some labeled data. Okay. Now coming to the models. Because with the data, what we do, we are talking about functions. Those functions, we are learning the parameters on these functions. Now, these parameters can be a finite set of parameters or an infinite set of parameters. So, with respect to that, also we can define the models. So, in parametric model, it's a family of distribution that can be described using a finite number of parameters. Whereas, in case of non-parametric models, the number of parameters grow as your training data grows. Okay. You can also classify machine learning with respect to their processing modes. Offline, in case of offline, the data processed after getting the video segment to be analyzed, whereas in case of online, you do the analysis as and when the data arrives to you. Okay. Now coming to that how then machine learning is different from the deep learning. So when people have started using machine learning with the help of say neural networks, then there were certain restrictions. Okay. And also due to the unavailability of high computation powers, people could not realize that if we basically apply these convolution operations in two-dimensional or three-dimensional, what will happen. Okay. So in convolutional machine learning methods, it primarily relies on human designed feature representations in conventional machine learning. Okay. Whereas in case of deep learning, we actually do not rely on human designed feature representations. Rather, we would extract the features through some operations. Okay. So in conventional machine learning, so the objective is primarily optimizing the weights to make the best prediction. Okay. Whereas in case of convolutional neural network or deep learning based networks, what we'll see, the number of parameters will be pretty high. Let's see this with respect to deep learning. So it is also a class of machine learning, which is, or you can also call it a subfield. So that uses multiple layers for learning data. If you see on in the top image, so there is a car image. So there is one person who is sitting here. That person actually is describing the appearance or characteristics of the car. It may say that, okay, this is an object with 4 circular wheels with this much of this type of shape, this color, everything that is basically is called feature extraction, manual feature extraction. Manual doesn't mean that somebody will write manually, but obviously with some mathematical functions. For example, you can apply age detection technique. You detect circles, you detect curved faces, and then you come some sort of representations of those objects or smaller objects and make a feature vector, and then you apply a simple classifier. Whereas, and classifier can be car and non-car, so that's using multi-layer perceptron you can do it. Whereas in case of deep learning, what you do, this intermediate person who is basically doing the feature extraction into the machine learning is replaced, and you do the feature extraction using the convolutional neural network. So this part tries to establish the relations between various points of the objects and try to explore all possible relations, but all possible relations is a very extremely computationally hard task, but whatever you can do it, you can apply it here. So this is the primary difference of deep learning and machine learning. Okay. Let's say take a more realistic example with respect to image processing, because I shall be talking more about image processing. So deep learning applies multi-layer process for learning. Multi-layer means it will extract features at various levels. Okay. So like it may extract low level features like, filter responses or ages. Okay. It may also extract mid level features like textures. Okay. These are the textures, patterns. It may also go for high level features where it basically extract object level information. Now, if you combine all these three together, you get a representation of the whole image here. And then it gets, the feature vector is basically used to train the classifier. This is what is done in typical deep learning frameworks. Now, you may do multiple you may use multiple layers of low level features, multiple layers of mid level features, multiple layers of high level features. This is very common, and this is not that difficult also because of the availability of the computation hardware. So from the input image pixels you detect so these are the raw. From there you detect the age, you also detect the texture, you also detect the parts, then you also detect the objects, which is finally our objective is to try to identify that what are the objects present in the scene. Okay. So then why deep learning is useful? It actually provides a flexible learnable framework for representing visual, text, linguistic information. So it can even learn in supervised and unsupervised manner. And but one thing is that it requires a large amount of training data. Okay. So approximately 10 to 15 years back, they explicitly mentioned 2010, but even deep learning also came slightly earlier than that, when actually GPUs started coming. So people thought that why not to basically apply the multi-layer convolution and neural networks to see that whether they can outperform the machine learning techniques, conventional machine learning technique. Okay. And they started applying in vision and speech and NLP applications. Okay. So I will not go into this part because these are typical neural network based things. I think many of the other speakers might have talked about the neural network based conventional neural networks and how it basically works. Basically, how the feature extraction happens from the low level to the representation. So these are very trivial things. How do you basically estimate that whether this is digit 2 or digit 1? These are very trivial way to explain typical neural network and its function. Okay, so I will basically skip these slides, but you can understand that this is basically a mathematical function. So 2 to the power 2 to the power R256 to R10. So you have 10 levels. So 0 to 9 are the levels, and you have 256 basically 8 cross 8 matrix, or maybe the more than that value. So you have a feature vector which is basically starting from x1 to x256 after doing some operations, obviously, or convolution operations. So basically this function, we are learning the parameters of this function. So if a feature vector comes like this within this space, whether it will be mapped to R0 or R1 to R10 or R1 to R10, any one of the values. So this is basically the function AF is represented by a neural network. Okay. Now there are elements like all these basic elements of neuron. I will simply skip these slides because this is not needed, I understand. So how the weights are decided. So basically we learn these weights with this, and also we apply certain bias so that we ensure that the activation function ensures that for a particular input combination what should be the output. So these are all the basics of neural network, and you can actually do it at multiple layers. Okay. So these weights, learning of the weights, this happens during the training process. So as you have more number of samples during the training, these weights get better to find. Okay. So and obviously depending on the number of parameters. For example, for a very small, example with 6 neurons, not, you can actually get, 26 learnable or trainable parameters. So all these 26 parameters need to be estimated. Now, this is a very small number, but actually when you extend it to multiple layers, okay, where many hidden layers are there, the trainable parameters may be millions or maybe billions. Okay, this is where basically we require a lot of data to train this parameter. Parameter means basically nothing but these weights values, all these transition weight values. So how do we basically use it? Okay, so like this is nicely explained that basically in this example, which I have taken it from some of the popular lecture series, you can understand that how basically these weights, initial weights, are actually updated with respect to a certain function. So for example, here we are using a sigmoid function, but how the weights get converted. So this is a very classical example which you can look into it and you can see. Now, the primary objective is that how basic of this today's talk is, we'll show that how machine learning and deep learning can be used for visual surveillance and computer vision related applications. That is our objective today. Okay, so this is where we shall start now to understand that how AI and machine learning can be useful for visual surveillance tasks. So one of the, I will show you from this slide onwards, I'll show you some applications of computer vision and visual surveillance in applications of AI and machine learning in computer vision and visual surveillance. In visual surveillance is like we can apply it in public places, we can apply it in private locations or restricted zones, we can apply in defense, we can apply in healthcare, we can apply in agriculture also, security monitoring applications, which are primarily using computer vision based monitoring systems. So let's start with deep learning for crowd tracking, because crowd is a phenomenon that we often see in our country. Talk about rallies, talk about marathons, talk about festivals, cultural festivals like Rath Yatra, Durga Puja. These are all popular events that happen every month, probably every week in the country, across various cities and villages. And because of the availability of the technology, now we can apply surveillance, machine-based surveillance, to understand that whether there is going to be any problem during the gathering. Okay, so that is what our objective. Typically, what happens in manual monitoring, what we require precise human efforts. Now, this precise human effort means somebody here is looking into the CCTV videos continuously and basically trying to identify that something wrong is going on, which is tedious job. That means it is error prone, because we are all human beings. Even if we try to do it, we may lose attention and we may not be able to pinpoint when there is something wrong going on. Okay, and also it is time consuming. Okay, on the contrary, if you look into the computer vision based monitoring based things, where it requires lesser human effort because your sensors will do it. Okay, and the back end there will be computing servers which will be doing it. It requires lesser human efforts. Lesser human efforts in a sense that even though at the back end you need somebody who will be basically running those algorithms, but in terms of direct observation which we are seeing it here, obviously that may not be required. That level of human supervision may not be required. That's why it is called lesser human efforts. Better information fusion means you can use information collected through various means, like not only camera, you can record sound also, you can record motion sensor data also, you can record hundreds of other sensor data available to you, and then you can fuse them to get more accurate decision about a scene. Okay. It can process high volume of video at less time. That is because you require more processing. You deploy more cameras, deploy more servers which can process your data. Also, the last one, even though it can be debated that whether it will be prompt, accurate, and intelligent, that's debatable. But we have seen that for some applications, they can actually compete with the human supervision based techniques. Okay, so that's why computer vision based monitoring is becoming very popular. I'll show you some latest research work that we are carrying out at IIT Bhubaneswar with my research team. So how it can be useful. Okay, for example, this is one. I'll show you a dense crowd characterization mechanism where basically we simply use optical flow. We don't use deep learning at this stage. In the initial stage, this is typical machine learning part where we use physics. So physics means we use like entropy, we use kinetic energy, we use Gibbs entropy, we use Langevin model. Okay, in the next I'll show you. And then we also use Brownian particle motion characteristics, and then try to understand that how can I model the gathering, dense crowd behavior, we model, the water flow, or we model the flow in air, okay, or free space. So here, very simple pipeline, like you have a video, you basically calculate the optical flow, and then you do some quantization, orientation quantization, which direction the pixel or the point is moving, and then do some local region analysis or connected component analysis, and then you find energy, entropy, and you can perform the analysis. So for energy calculation, you can simply use motion, because you know the optical flow. So energy of a pixel, or you can consider as a moving point, can be approximated by the velocity with half mv square. You basically ignore the half part. So, and assuming that each and every pixel is having a unit motion, unit mass, so you can take the energy as of a pixel is average of v square. Okay. Now, if you do it for the all pixels within a frame, then you can get the average energy of an image frame. Okay, and that can be a parameter to understand that how dynamic the image is, or how dynamic the particular frame is. Then similarly, you can also look into the entropy part. Okay, so entropy, where we have explicitly used Gibbs entropy. There is a reason that why you have used Gibbs entropy, because it basically with certain relaxation, obviously. When Gibbs entropy is applied to Brownian particle or fluid, it may not be similar way we can apply to the human crowd pixels, but with certain restrictions you can put it. Okay. So considering each connected component as a microscopic state. Microscopic state means they are basically within a local area, and their dynamics are not changing instantaneous. We can assume that their dynamics is constant within that region. And the whole frame can be considered as a macroscopic state. So basically, you assume that, say, if I use a pin, say you have a frame like this, and you assume that these are microscopic states. Okay, so they have directions like this. So it's not a single pixel. These pixels may be grouped together, and then it will be just a minute. I need to take this call. 1 minute. I'll take this call. Yeah, sorry. So, so this is. Am I audible now? Sorry, I had to take that.
Yes, sir, you are audible.
Yes. So, if you see, when we apply this kinetic energy and entropy, we get characteristics, local characteristics of these groups at the microscopic level as well as macroscopic level. And then when we plotted this on a video like this, we found something interesting. Interesting in a sense, we can see that for a crowd like this regular movement, the entropy is constant, even though it is a little higher, but entropy is almost constant. You can see in the top, whereas the energy is slightly varying, but energy is low. Okay, Now see, when the crowd is something like this, okay, this is where basically it's more dynamic. Okay, you can see that entropy, even if it is higher, and it is fluctuating, and energy is highly fluctuating. So it means we can probably say that, at least with respect to the videos that we have looked into it, that if significant fluctuations are observed in interframe energy, it can be attributed to a fast moving crowd with a higher velocity. Okay, whereas if the fluctuations in interframe energy difference are low, then the crowd can be assumed to be moving at a uniform but lesser velocity. Okay. Similarly, more fluctuations in the entropy curve indicate varying randomness in the crowd. Okay. And for constant entropy, the randomness can be assumed to be less. Again, these observations are only with respect to certain videos. We cannot generalize it, but in research, it is extremely difficult to generalize certain things when we are using approximation. Okay, but at least when we applied it on a decent number of videos for a long run, we found that these are the characteristics. Now again, going ahead, we actually try to understand that what is happening within this microscopic group. Okay, let's say if we would like to compute the optical flow in each and every frame, it will be too much computation intensive. Why not to do it at certain intervals and use some physics law to assume that within this duration it doesn't change. So for that, we actually took the help of a popular model that is called Langevin equation, okay, which is based on Brownian particle motion, Brownian particle. Okay, so how the Brownian particles behave? Let's assume look into the right side picture where there is a Brownian particle here. What are the different forces that this particle is basically getting experienced? One is the random force, okay, which is a green force. Okay, the Newtonian force, which is red because of obviously the attraction and repulsions. Okay, so these particle P will be attracted or by the nearby particle. So that force is always applied. And the other one is the frictional force because of the motion. Okay, so this blue one is the frictional force. So with all these three forces, and okay, it is possible that you can describe the dynamics of a non-equilibrium system. It is probably one of the simplest way to describe the dynamics of a non-equilibrium system, where gamma t is the frictional force coefficient and zeta t is the random force arises due to random density fluctuations in the fluid. So basically, because of the random density fluctuation happens within a fluid, but obviously here we are not dealing with fluid. Again, I'll tell you, when we applied this on a crowd, we can't assume that they are fluid, because in fluid, its homogeneity is much more important, whereas in case of crowd, that homogeneity is not there, but with certain restrictions we did it. So when we formulated this, and so what we did, this initial microscopic group, we, instead of applying optical flow in each and every frame, what we did, that we grouped these microscopic areas, which are local regions, and then see that where these regions will be going in the next time frame. Next time frame means, say, because we have the force equation. With this force equation, if I know the current position, I can say that, okay, what will be the position of this group at some other point of time? So, or say 10 seconds from now onwards. This is what my objective is. So that we did it. And so if you look into this, this particular diagram, you will find that this particular part is the initial phase. Okay. Now, initially we do it for I, t less than equals to 1, t less than equals to 1. Okay, whereas from t greater than equals to 1 onwards, what we do, or say t greater than equals to 2, we do this Langevin model. So we don't compute optical flow in each and every frame, because that is pretty expensive. Okay, so we do it in some frame, and then we use this model, and then we do. And all the predictions, how do we get the new positions? Because we know the velocity. So from the velocity, you do the integration, you get the position. So this way it is possible to estimate the position of these groups. And assuming that within the short interval, the dynamics within the group does not change. That is what our assumption. So all these equation, mathematical parts and other things, you can look into our papers, which are there in pattern recognition and expert systems, the applications. These are a couple of years back publications, but these models work pretty well. Okay. So, and when we applied this on different type of crowds, say for example Puri crowd, then we also applied, took some publicly available data sets, fair data set, chuck data set. We found that this was performing good. So for example, this is the original image, then second row gives the ground truth. Ground truth means we have manually labeled it just for the comparisons, and when we did the segmentation, we found that it was doing better segmentation than the methods. Like for example, Ali's method was not performing that good. Okay, so this is again on a Rath Yatra clip where these data sets we actually created. So this was running under a project, ministry project. So we did it, and we found that the algorithm was working better for, at least for the, and also it was working fast, because our objective was to do it in real-time surveillance. So if you would like to do real-time surveillance, you should actually process at least 25 frames per second. Now 25 per second, frames per second, we can't process it using optical flow. So that is what we wanted to achieve, and we found some computational gain. Okay. Now coming to some other, so in the part which I was discussing about, it's mainly for dense crowd. Now dense crowd is one part, but often we also encounter situations where I would like to identify or track movement of individual people, okay, or individual vehicles or individual objects. So that's why the second part of this talk, well, I'll talk about AI models for moving object tracking. Here Arif was working. Arif, I think he gave a talk even in this seminar itself. He might have discussed some of these things. I'll touch upon these things before I move to another one, very recent work which we have been carrying out at IIT Bhubaneswar. So here in Arif's work, you might, I think Arif might have discussed about it. You see that where are the areas where we actually apply, and we got a lot of research publications, particularly in various IEEE transactions. Okay, so mainly we contributed here in trajectory extraction and selection, feature extraction and clustering, region of interest segmentation, abnormality detection, summarization and synopsis. These are typical video analytics framework you can talk about it, where you detect object, get the trajectory, make data set, extract features from the trajectories, do the clustering, then apply this 3, 4, 5. They are mainly applications. You can identify region of interest, you can do anomaly detection, you can do summarization and synopsis generation. So motion trajectory is nothing but a sequence of points in temporal domain. So okay, so it's defined by the position of an object in temporal domain. Like this way, you can see that it's triplet. Okay, so x1, y1 is the position of an object at time t1. And similarly, you can see that. So this T is basically the entire trajectory of the object. Okay. And now, if you represent it in different way, say for example, this is a two-dimensional representation. So when I superimpose this two-dimensional trajectory on the image, I don't get much information. Okay. Whereas because it doesn't tell about that what about the person's behavior at a certain point. So that can be, probably understood if I make a 3D representation. This is a very simplistic representation, just to tell that how that 3D representation can actually provide better information. For example, if you see here, so the trajectory, in the same trajectory, when it is basically plotted, we found that there is a constant, there is a change in time. Whereas the positions are not changing. So that means the person was probably standing somewhere here for some time. Okay, so this is what it can reveal. Okay, but there are certain challenges when we do object tracking. So it can be, occlusion is a challenge, scale of object can be challenged, environmental noise can be challenged, multiple objects may be challenged, fast moving object, dense crowd, which we have already seen it. They're all challenging situations. How do we handle all challenging situations? That's really problem. So now tracking is one domain where, even though we have not contributed explicitly in tracking, but we have used tracking in almost 80% of the research work that we have carried out at IIT Bhubaneswar during, at least in my lab, during last 10 years. Okay, so at least 70 to 80% time we rely on tracking. So tracking means object tracking, moving object tracking, whether it is dense crowd, sparse crowd, individual people, car, vehicles, other type of vehicle, animals, wherever we do video analytics, we want to track objects. So for tracking objects, you need a good tracker. So this is what we have done a little bit of survey. Arif actually did a survey on it, and we actually found that there are interesting tracking algorithms available, and some of them are pretty good. And when, like, so start with detection, because our objective was the earlier tracking algorithms, which were mainly physics-based tracking, they were not performing well. Okay, performing well in a sense, they were performing well up to a certain point. But when deep learning came, people have shown that the tracking performance can be substantially improved. So with the help of detection, that is what I'll show you. So that's why we start with detection. So how detection works here? So detection, so let's say here basically we have applied a simple YOLO model, even though it's a pretty old model. If you see the video, I hope that the video is playing. Okay, so the objects being carried out by the persons, you can see, even this girl is, you see that cell phone, it is able to detect this cell phone, even though the phone is not visible. Even though the phone is not clearly visible, it is possible for us to see that the model is basically detecting that there is a cell phone, there is a person. This is how, now this is version 3. Now we are using with version 7. Okay, so you can understand that the detection performance has improved over time. This is 3 years old. Okay, so the detection for object detection has improved a lot during the last 10 years or so down the line, and it has reached a level where we can very accurately detect even tiny objects, okay, which are very small, and even the background is cluttered and lighting condition is poor, still we are able to detect. That's because of the emergence of the complex deep learning models for object detections, okay, which is primarily the content of YOLO and the successive versions of YOLO. And we also tried, this has been applied on our datasets also, IIT Bhubaneswar datasets. We were able to detect objects from various angles at various, here mainly object means human objects. Now you can simply look into a method. Now we have detected objects in each and every frame. Now can I apply a simple tracking algorithm? SODT is a tracking algorithm which was, even it is also 6 years old. Now there are better tracking algorithms, but why I'm showing it, just to tell you that how people have actually applied object detection and track and then perform the tracking algorithm. Let's see with this example. So if you look into it, we have a video and we extract the frames. Now here I'll be showing you with respect to 2 frames only, say frame I and frame I+1. So if you apply object detection on both the frames using YOLO version 3, okay, you get certain detections here also, here also. Now you do next level, what you do association. Association means, because you have detected 2 regions, bounding boxes here. Now whether this region is matching with this or this region is matching with this. Similarly, whether this region is matching with this person or this region is matching with this person. These are the questions that need to be answered. Now the second part in this paper, actually, I see 2017 paper, they actually talked about association based on appearance cost. Okay, and they basically performed the association with respect to appearance cost and designed the tracker so that they maintain the level. Now they are maintaining the level. 20 is 20, 15, 15. So these were in the frame number I. This object was labeled as 15. In the frame number I+1, this object was also labeled as 15. So if an object is labeled with the same number over the time, that means you were able to track it. That's very simple. And this is a very simple paper, and it was able to detect the object. And then there are many variations came. I will not talk into those variations, but there are many variations. When we applied this on, say, on our data sets, it was able to track people. So now you see that these numbers are printing now. So numbers means that this person is detected. Similarly, even though sometimes it fails, but it is able to detect people uh, more accurately. Now, multiple persons it can detect. It can detect multiple persons. Then we checked it with also publicly available data sets like PATS 909 data sets. Then we have applied it on town center data set, and these performances are not bad. I mean to say that even though it has improved over time, if you look into the state of the art, today's state of the art, you will find better tracking algorithms. But why I'm showing this, that the tracking performance has improved over time. And if you basically look into the every year's CVB or ICCV conferences, you will find more accurate tracking algorithms are coming, even though it has reached a saturation where people have assumed that the tracking has attained a substantial accuracy, and people have shifted their focus from tracking to maybe more deeper analysis. Okay, so these are some more examples with publicly available data sets. These are challenging conditions like camera positions varying, okay, from top, from bottom, side, background is changing, everything is, their occlusions. For example, here you see that this person is occluded again. You see here this person goes, even the occlusion, you see here, if you see, person is 2, 2, 2, 2, 2. You see, this is what that means. The appearance based cost was actually performing well, because the appearance did not change it. And the similar concept is actually used in also another problem, which is re-identification of a person, which is extremely important with respect to the surveillance perspective. And I will show, if time permits, that re-identification is one area which is heavily being studied by the researchers during last 4 or 5 years. Okay, and these are some more examples of the tracking. Okay, so these are all different, and you see that complex people are actually gathered in the same time and same place. So now comes the multi-object tracking. Multi-object tracking, even though this is basically a kind of branch of tracking. Here actually you know, uh, people have started employing more complex networks. Okay, like adversarial deep tracking, they have used, RESTnet as well as, CNet to combine them the results. So these are all variations of tracking and which are pretty common. Okay. Another way of tracking comes unsupervised tracking, where in the tracking that we were talking about earlier, they mainly do the detection first. So you do the object detection and then apply some heuristic or apply some logic at the next level, so that you basically associate these objects with the levels, and then you perform the job. Whereas in case of unsupervised tracking, you do not know that who is there or what is the object. So you don't detect the object rather, but you do tracking. So we also did some work, which one of my PhD student was working here. He was completely working on mathematical modeling of, of unsupervised tracking. So we have used we have actually came up with a model that's called modified Dirichlet process mixture model, which is a complex mathematical model, obviously Bayesian probability based model, where we represented the states of these objects with respect to parameters. Okay, now these parameters are estimated from the appearance, not from the known appearances. Okay, so we grouped the pixels and then understood that how the grouping changes over time. So you can actually find out these details about these papers into this about this method into these papers. Like this is one paper, but we have a couple of more papers in the transactions, cybernetics also. So where we found that the tracking, even though it's not machine learning or deep learning based tracking, it is basically you can say that conventional way of tracking, but it actually outperformed popular algorithms like mean shift, KLT, which were popular. Okay. Now, I will not go much details into those models. Those who are interested, they can actually look into our papers. This one, as well as there are some more papers related to which are done by Dr. Santosh. You will find in my website, which are pretty recent actually, maybe 2019, 2020, 2021 papers, even 2022 papers, where you will find that how mathematical models can be used to identify patterns within an unknown set of trajectories. Okay, these are pretty interesting research work we carried out. Now coming back to another application of the tracking. Now we are going to the application part. So we talked about the basic of object detection. We talked about basically the object tracking. We actually need to see that how this object detection and object tracking can be used for real applications. One of the applications is visual synopsis. Or if I was working with this, I'll show you some examples at how visual synopsis can be generated using this. Okay, so here again, this is a generic framework where basically we do recording, background extraction, object segmentation, object tracking. We create data sets, tube data sets, but then finally we would like to generate synopsis. Synopsis is a thing. Let's say you have been given with 10 hours of video, but you do not want to browse the whole video. You just want to see that important portion of the video, maybe in 1 minute, 2 minutes. Okay, so that is what called synopsis, and this is an interesting domain of research which is required mainly in security, surveillance, highlight generation, okay, and many other applications which are it can also be used for entertainments. For example, I did not watch yesterday's cricket match when India was playing in the West Indies. So today morning I woke up and I wanted to see only those portions where, say, Yashasvi Yashwal, he was batting. So is it possible that automatically I get a synopsis based on my request? That is what is more customized synopsis generation. So Arif was working on a problem where basically he used a very simple shallow neural network which can actually classify 3 objects like a car, bike, and pedestrian, and try to generate synopsis that will be meaningful to a particular office, say for example an administrator. Okay, so I'll show you. So this is a very very shallow conventional CNN architecture. There is nothing new here, but what I'm trying to show you, with the help of this object detection and trajectory extraction, we are able to basically generate the synopsis in a better way than what people were doing earlier. Okay, so here you see that we recorded videos inside our campus and then we identified these locations, okay, where these trajectories actually entered into the scene. So this green, red, blue, they are nothing but the entry points of the trajectories, and these are clustering. Okay, with respect, with the help of simple clustering, point-based clustering and region, similarity-based clustering, we found that okay, these are the regions where the trajectories actually entered into the scene. So then we actually generated some scenarios like, if I want to see all the trajectories which are basically entering from blue or entering from green or entering from red region, Similarly, exiting through blue, exiting through green, you can get all the combinations like red to blue, blue to green, green to red, all combinations you can find it. Okay, and then you basically do the synopsis generation. Now, in the synopsis, what we would like to see, that because it was say maybe a couple of hours video, I do not want to see the videos fully. I want to rather see only only the important portion of the video, which is basically important for an administrator to take some decision. Okay, so like say somebody wants to see that I want to see a white car which has entered into the scene, and I want to see only its appearance and related time. So similarly, I will show you a very broad level query here, where basically see the car. If I play the video, it will only show you car like even if this is a bus, we assume that the bus is a car. You see, so you see that sometimes the bus is disappearing. It means it's the algorithm is still not correct. Okay, but it will only show you this car has appeared in the scene, whereas this car has appeared at 8:52. How can they be available and be shown at the same time? That is what called synopsis. So it's a spatiotemporal optimization. So we detected all the vehicles, we placed the trajectories of the vehicles, and then we did the spatiotemporal optimization, and then we actually generated these foreground or pasted these foreground objects on the background, keeping the background fixed, and created a video. Okay, so that is what we did it. And even though it is not perfect always, you can see that there are some effects like spurious objects are coming and some objects are appearing, disappearing. But what it shows that it is possible to generate such synopsis with accurate details of the objects of your interest. Similarly, this one talks about the bikes. Okay, it only shows the bikes. It will not show anything of the same video. So it is automatically generated. It is not manually generated, automatically generated from the raw video. Similarly, this one, it is only human being. So it will only show human being of the same video, from the same video it is shown. Okay, and different time interval. You see that this person is at 8:49, this person at 9:12. How can both of them be together? So that's because I do not want to see the whole video. Like wrongly this car came, it is detected as a human. So this is something wrong. But most of the time it was giving actually good results of detection of objects, detection of human being, detection of cars. So and what we have generated, like this is basically, you see 1 minute 25-second video, 1 minute 25-second video for pedestrian. But if you look into the original video was more than 3 hours long, I understand. Okay, so from 3 hours we actually created a couple of minutes video. And this video was which we wanted to generate to understand that how actually objects behaved during that time, particular type of object like cars or two-wheelers or human being or even other type of objects. So it all depends on what basically you have. Here basically we have used the 3-class classifier. If you want multiple classes, you just increase the number of classes. That's it. So the network can be trained with more number of classes. So you get it. So this is possible to extend the same architecture to be applicable to more than 10 classes probably. Okay, and you train it and you will be able to do it. So irrespective, even you don't need to basically rely on this particular geometry of the scene. Like you have a scene where there are 5 entries, you have a scene where there are 2 entries. It is possible. So that is what basically we call rather a generic framework where basically the algorithm will work. And this is what I actually did this one. This was pretty interesting, and I thought that let me share with this. The next part of the talk, or the final part of my talk, I'll take another 10 minutes because I have another meeting at 4:15. So this is talking about video object tracking for traffic applications. Now, because we started with the object tracking, now object tracking is basically the primary clue, or I'll say the prime or the initial step of many of the visual surveillance applications. So in object, once we do object tracking, we can perform synopsis generation, we can perform traffic applications. I will show you some more applications here. So object understanding and classification for traffic applications. So for example, how the this is this particular slide, it talks about object localization using in an unsupervised way. We don't detect it as a car, we detect it as a blob of pixels and its motion. Okay, so this is a cluster frame. We actually find out the clusters, which are the local clusters. Local clusters means their appearance may be same or characteristics may be same in terms of motion dynamics and appearance dynamics. Then we did an object level fusion. Here itself we found out the object. Then we basically did a class frame. We found out that what is this class. We even applied it on trajectory to identify the class, to identify that whether it is possible to do it on a traffic signal or not, and whether we can do it on tracks or not. For example, if you look into this, the left corner, top left corner, these are all trajectories. These trajectories are raw trajectories. What we did here, again, Dr. Santosh, he worked on this. This is an interesting work where we basically clustered these trajectories, and this clustering is not by source and destination. Source and destination clustering can easily be done. You don't need a machine learning algorithm to do that. But here what we did a spatio-temporal clustering. That means if a vehicle moves from here to here, if you see, this is a changing gradient, color gradient. It's not a single color. Even on a single trajectory, the colors are changing. The colors are changing, particularly you see that this is more visible. This direction more visible. Now from orange color to green color to blue color to pink color, this change is not to show that the object is moving from here to here. It is also, this color also signifies that at what time these movements are happening. Why this is happening? That will be helpful for traffic signaling, because it is possible that when a vehicle actually moves from here to here at 9 o'clock in the morning, it will take longer time, but when it at 1 p.m. in the afternoon time, or maybe night at 12 a.m., it will take lesser time because of the traffic density. So this is a complex mathematical model which you can look into our paper in IEEE transactions and cybernetics, where basically, now see, its real application comes here itself. This is a CUHK data set with more than 50,000 trajectories. We can't do anything with this set of trajectories. But what we discovered with these trajectories, these are the prominent patterns. These prominent patterns, these are spatio-temporal patterns. So like cluster 26 is a highest prominent pattern. It means, it says that out of all these 50,000 trajectories, there is something happening from this region to this region. So probably this was the entry point of the metro station, and this probably the exit point of the metro station. People have entered or exit from the train, okay, and the exit from the metro station. So this probably is one of the paths. So, and some other prominent cluster also. It means, and this data is not 1 hour data. It was data for maybe 7 days time, and we wanted to understand that whether this spatio-temporal clustering can be useful for finding out the detailed dynamics of a scene. Okay. Then the last part is how we can use this trajectory information and other appearance information for doing the video anomaly detection. Okay, like Arif was working in one of that part where he has used different type of tracks and then identified that, okay, this particular track is illegal track, or this is a illegal U-turn. Okay, so abnormality is illegal U-turn can be an abnormality. Somebody has parked the car on the road, middle of the vehicle, suddenly that can be an illegal. So this is what we have also done it. And finally, we moved very recently means only last year onwards, we have done a few publications where you will find that we wanted to detect accidents on road. with the help of same tracking based mechanism. So here in this work, which is ongoing work, and some of the publications are already there, where you will see that we detect accidents instantaneously and we highlight it and we describe the accident. So this overall framework, it's not only we detect vehicle to vehicle, we also detect vehicle to pedestrian collisions, we also detect pedestrian to pedestrian anomalies like pedestrian illegally crossing, pedestrian fighting on the roads. So these are more detailed descriptions of the event happening. Okay. So one of the research work which was published couple of years back, where basically we created the model, machine learning model, where basically it is able to highlight the portion where the accident is happening, as well as it is able to create a description of the accident. So this is the description of the accident, like how, at what time of the frame, how many objects, what are the type of the object, what is the area of accident. So all this automatically it is able to generate. Now this whole pipeline is a little bit complex pipeline, which uses couple of architectures and couple of deep learning networks. You can look into our ITS papers and pattern recognition papers and other high rated conference papers, but there we did it. Now I'll show you, I'll stop with these examples where basically you can see that these this generation is automatic. The text generation here, it's automatic. So that means it says that, and the accident happened, you see this highlighted portion. Okay, final highlight, basically final heat map generation comes here itself. Now another example, say for example this one. You see, it will give you instantaneous, then it will, at the end you will get the final output here, and it says that there are 4 objects, 2 cars, 2 motorbikes, 19% of the accident area was so basically this can be used for estimating the damage. It can basically, this information can be directly sent to the police to take immediate action, or to the medical team to take immediate action. So we applied it on different scenarios like night scenarios and also critical conditions or difficult situations. We found that it is able to describe the events in a better way. Okay, so this is the last slide where I will show you that how the accident can be detected. So I'm showing only with the public data sets available. We have also created a lot of data sets at IIT Bhubaneswar and Bhubaneswar areas, because these are all funded projects. And we have started doing even deeper analysis. People who are interested to know more about this, I have whatever up to this slide I have discussed about 2021. 2022, 2023 research papers I have not put into the slides, because they are even more latest state-of-the-art research paper, where we detect accidents without even training the system with real-life accident videos. Okay, so this sort of research work, which probably in one of the future lectures, if possible, I'll tell how it is possible, even because you don't get these sort of videos every day, and if you don't get data, then how do you train your model? So what we are doing now, that without even having the real accident scenarios, we are able to generate models which can detect accidents with synthetically generated video data sets. So that is what the latest research work which we are carrying out at IIT Bhubaneswar. And with that, I will stop. I would like to thank my students, Dr. Arif, Dr. Santosh KK, Dr. Sritam, and Kamlakar, last work, who has also submitted his thesis. He is waiting for his thesis defense. So all of the work which I have presented today, they are primarily worked by my PhD students who worked with me during the last 5-6 years. And with that, I will stop here. I have a couple of minutes time to take questions.
Okay, so thank you, Dr. Dogra, for that very informative talk on applications of AI and ML for visual surveillance. So I have posted the questions on the chat box, because most of our participants, we are streaming this event on the YouTube channel, and most of the participants are there, and they are putting questions there. And I have copied all the questions from that YouTube channel to the Google Meet chat box. You can find the questions.
I can see the questions. The questions the question from one participant is how complexity will increase in multi-environment, multi-object moving objects of different type. So the complexity will not increase because see, this is another project which we have started doing it because different type of objects are involved in different types of anomalies. So multiple objects are involved in multiple type of events. So obviously complexity will increase, but because when we talk about deep learning framework, they consider the whole frame. So maybe we need separate attention models. Okay. So that is exactly, you rightly pointed out, we are actually working on it. Complexity will increase, but our objective is to ensure that it does not increase too much so that we will not be able to do it on real time. Okay. So obviously, if you would like to do multiple detections, multiple tracking, it will be a little bit, computational load will increase. But with the availability of multiple multi-core architectures and efficient algorithms, it is not a difficult job to handle. The second question is, what about if the quality of the video is not good enough to identify the objects? That's another valid question. I mean to say, if you look into the latest researches on diffusion-based architectures, they are able to even generate high quality from the low quality. So I don't think that low quality videos is a problem. We have tested with our synthetically generated very high quality video and also tested with real life low quality videos, because real life videos are mostly recorded from the CCTV cameras where the quality of the video are not good. So it is possible to generate high quality videos from there itself with the help of diffusion networks. Okay. Then can we use high definition cameras? HD cameras, you use it, but that will increase the load, computational load, like I already talked about in our synthetically generated videos. If you look into our website, my website particularly, couple of research work which we just published 2 months back, we used synthetically generated high resolution accident videos to describe accidents. Now, while the paper was under review, the reviewers actually questioned these sort of things. So we defended it. The reviewer also had the same question, that do you require high definition videos or high definition camera? Probably in some cases required. Say for example, I want to detect the number plate, okay, in an accident, that who is involved or who is inside the vehicle. I need to use a high definition camera, obviously. I can't do it with a low definition camera or low resolution video. So these are all trade-offs. You'll have to make a trade-off, which is more important for you and which is not important. So the next question is there any specification in the frame size? No. For object detection, even we do it with a very low resolution videos like 320 into 240 resolution videos. But if you have higher resolution video, obviously the system will improve. The next question is there any specification in the frame size? So that I have already. We should have clear objects to track. How to categorize the cluster frame? Clear objects to track. Yes, clear objects to track means the object is clearly visible. In some cases, that's why the motion is important. If the object's appearance is wrong, but if you know the motion pattern, probably you can refine the detection algorithm. How to categorize the cluster frame? How to categorize the cluster frame? So that's more mathematical in nature. I would suggest you to go through our IEEE transactions on cybernetics papers written by Dr. Santosh KK, which was published in 2020, I understand. They are actually discussed the mathematical model of the clustering algorithm, which is a little bit complex one. But if you study the paper, you will get the idea. If you have any doubt, you can always send me an email. I'll try to help you to understand the algorithm. Okay. So I don't see any other question.
So no other questions. So on behalf of the organizing committee, I convey my deep regards and hearty thanks to our speaker, Dr. Devi Prasad Dogra, for delivering his valuable talk on applications of AI and machine learning for visual surveillance. I would now would like to present a small token of appreciation to our speaker, Dr. Dogra, a certificate which I'll share here. Payment. So, Dr. Dogra, this is the certificate which is being presented to you.
Thank you all.
Okay. So now I would invite Dr. Shubhankar Juardar, Professor and Head of Computer Science and Engineering, and who is also the program chair of this event, to deliver his vote of thanks.
Thank you, Professor Barman. It is my privilege to have been asked for the vote of thanks. This is a momentous day for our department, as we have hosted this grand faculty development program. On behalf of our department, I would like to propose a vote of thanks to our more than 500 participants across India, from various streams of education, from research to science and technology. On behalf of the CSE department, I extend my very hearty thanks to all our honorable speaker. From day one, Dr. Siparna Shaha, Associate Professor, Department of CSE, IIT Patna. Day 2, Sanjay Kumar Panda, Assistant Professor, Department of CSE, NIT Warangal. Day 3, Mr. Shubhro Sarkar, Principal Consultant, Cloud, Tech Mahindra. Dr. Sheikh Arif Ahmad, Assistant Professor, School of Computer Science and Engineering, XIM University, Bhubaneswar. Dr. Professor Devi Prasad Dogra, Associate Professor, School of Electrical Science, IIT Bhubaneswar. I must thank Professor Devi Prasad Dogra, who blessed us with his presence and took out valuable time of your busy schedule. Thank you, sir.
Thank you, sir.
Thank you to our patron, Delete Dr. Lakshman Chandra Seth, Chairman ICARE Haldia Institute, for hosting this 5-day faculty development program. Our patrons, Mr. Ashish Lahiri, Secretary ICARE, Mr. Shantan Seth, Vice Chairman ICARE Haldia, and Mr. Shodiktan Seth, Assistant Secretary ICARE Haldia. I also thanks our advisory committee, our organizing chair, Dr. Pinagipati Macharjo, Dr. Shantanu Kole, the whole organizing team. Thank you all, and thanks to the participants for enormous amount of participants to participate in this faculty development program. Near about 600 students, faculty, students, researchers, they attend this faculty development program. From the core of my heart, thank you, all of you. Thank you.
Thank you, Professor Jordan, for that vote of thanks. So today, with that, we conclude the week-long faculty development program with plenty of learning for the participants from institutions all across India. So the objective of the FDP was to present a clear understanding for today's technologies based on next generation smart computing paradigm. Prominent interactive sessions with experts were held in different domains of research, such as cloud computing and its services, fog edge computing and its applications, Internet of Things, big data analytics, artificial intelligence, and many more. So we hope to organize more FDPs in the years to come. With that, I'm signing off. Thank you.